Welcome to this exciting journey into ring theory. Today, we are going to explore a fundamental and fascinating concept known as the characteristic of a ring. It is a beautifully simple idea that reveals the hidden geometry and structure of how numbers behave when we add them together in different mathematical universes. Let us dive right in and build our understanding from the ground up. To truly understand what a characteristic is, let us first imagine a standard 12-hour wall clock hanging in your room. If you start at midnight and keep adding hours, you eventually hit 12, which resets your position back to 0. The clock loops back on itself. Now, imagine walking on an infinitely long straight road. If you take steps forward, you just keep going forever and never return to your starting point. In mathematics, the characteristic of a system is simply the exact number of steps it takes to loop back to 0. Now that we have the intuition, let us look at this visually. On the left, you see a circular clock face, representing a system that wraps around. Here, taking a certain number of steps brings you right back to 0. This system has a non-zero characteristic. On the right, the straight number line stretches on infinitely. No matter how many steps you take, you never return to 0. We say this system has a characteristic of 0. This visual intuition of looping back leads us directly to the formal mathematical definition. In any mathematical ring, the characteristic is defined as the smallest positive integer, let us call it n, such that adding any element to itself exactly n times results in the number 0. If the ring has a multiplicative identity, which is an element that acts exactly like the number 1, we only need to look at that specific element. We just add 1 to itself repeatedly until it magically vanishes into 0. So, how do we write this looping behavior mathematically? We use a very simple and elegant equation. N times 1 equals 0. Here, the variable n represents the characteristic we are trying to find, which must be a positive integer. The symbol 1 represents the multiplicative identity of the ring, and 0 represents the additive identity. It is crucial to note that the dot here does not mean normal multiplication. It is a shorthand way of writing 1 plus 1 plus 1 repeated exactly n times. As n increases step by step, we check if the sum hits 0. Before we move on to more abstract ideas, let us see this formula in action with a concrete example. Let us find the characteristic of the ring of integers modulo 6. This specific ring consists only of the remainders from 0 to 5. Our strategy is to take the multiplicative identity, which is 1, and add it to itself repeatedly. Adding 1 copy gives us 1, 2 copies give us 2. If we keep going up to 5 copies, we get 5. We are still not at 0, so we must continue adding. Continuing from our previous step, let us add one more copy. We have now added 1 to itself 6 times, giving us a normal sum of 6. However, under the rules of modulo 6 arithmetic, the number 6 is equivalent to 0 because the remainder of 6 divided by 6 is 0. Because it took exactly 6 additions of the identity element to reach 0, the characteristic of this ring is 6. Now that we have successfully solved a simple modular ring, let us look at a slightly more complex scenario, finding the characteristic of a direct product ring. Here, we are pairing elements from a modulo 2 ring and a modulo 3 ring together. The multiplicative identity in this new paired ring is the coordinate pair 1, 1. To find the characteristic, we need to find the smallest positive integer n such that adding this specific pair to itself n times gives the 0 pair, which is 0, 0. Let us break down this equation. When we add a pair to itself n times, we distribute the n into the coordinates. For this pair to equal 0, 0, two things must happen simultaneously. First, N must equal 0 in the first ring, modulo 2, meaning n is a multiple of 2. Second, n must equal 0 in the second ring, modulo 3, meaning n is also a multiple of 3. We are almost there with our calculation. We need to find the smallest positive number that is a multiple of both 2 and 3 at the same time. In mathematics, this is simply their least common multiple, which is 6. Therefore, it takes exactly 6 steps for both positions in the coordinate pair to reset to 0 at the exact same time. This gives us our final answer, showing that the characteristic of this direct product ring is indeed 6. So, we have seen how to calculate the characteristic for different rings. This brings us to a very famous theorem regarding a special type of ring called an integral domain. An integral domain is a ring where multiplying two non-zero items never produces zero, much like normal numbers. The theorem states that the characteristic of an integral domain must be either 0 or a prime number. It can never be a composite number. Let us prove this powerful theorem step by step using a logical method called proof by contradiction. We will start by assuming the characteristic is a positive number n, and we will pretend for a moment that n is a composite number, just to see what goes wrong mathematically. Because we are pretending n is composite, it can be factored into two smaller positive integers, which we will call a and b. Both of these must be strictly between 1 and n. By the very definition of the characteristic, we know that adding 1 to itself exactly n times gives 0. Moving forward with our proof, we can substitute our factored version of n directly into the characteristic equation. Using these standard rules of algebra within a ring, we can carefully regroup this expression. Adding 1 to itself a times b times is the exact same thing as taking a copies of 1, taking b copies of 1, and then multiplying those two separate groups together. This algebraic manipulation leaves us with the product of a times 1 and b times 1 equaling 0. This sets up the crucial step for our contradiction, which we will resolve on the next slide. Here is where the unique magic of the integral domain comes into play. We have two items multiplying together to give 0. But remember the golden rule of an integral domain. Two non-zero things can never multiply to make 0. So either the first part is 0 or the second part is 0. But this creates a massive logical contradiction. We defined n as the smallest possible number of times you add 1 to get 0. Since a and b are strictly smaller than n, they cannot possibly reset the ring to 0. Our initial assumption was completely false, proving the characteristic must be 0 or a prime number. Now that we have proven this fundamental theorem, let us understand why the characteristic is incredibly important in the real world. It dictates the fundamental shape of the algebra. For example, in a ring with a characteristic of 2, 1 plus 1 equals 0. Which implies 1 equals -1. Addition and subtraction become the exact same operation. Because computers operate on binary data, algorithms used in cryptography, like AES encryption, rely entirely on rings with a characteristic of 2. Let us summarize the key takeaways from our journey today. The characteristic of a ring tells you how many times you must add the identity element to itself to loop back to 0. If it loops back, it is a specific positive integer. If it stretches infinitely, it is 0. We also learned that in an integral domain, this number must always be 0 or prime. You have now mastered a powerful concept that describes how addition behaves inside any mathematical universe. Great job!